All right. Thank you. I am Andrew Buck. I'm from the University of Missouri, and this will be our talk. So, first of all, I want to start off with just a very basic understanding of why we did this study. So, first of all, we want to have a 3D simulator for generating synthetic data with ground truth. 3D simulation environments are really helpful for a lot of things, as we all know. The particular problem that we were interested in is doing autonomy with drones. And so we've used Unreal Engine and AirSim to model environments where we get color images and depth images and segmentation images. And we can actually project those out into really accurate 3D point clouds. And this is something that I want to focus on today. So if we actually look at that point cloud, we think of this as ground truth. We say, hey, this came from a simulator. That's got to be super accurate, right? And as we use it more and more, we start to notice, well, there are certain times when there's points that don't quite match our intuition or things that don't seem to really be right. So as a kind of highlight the example, if we downsample that image and we don't quite handle the interpolation of the depth and the color quite right, the point cloud that we reproject, it has a lot of errors. So if you look at those stop signs, those poles and things, some of those points don't belong where they appear in that image. So this is something that we wanted to dig into in a bit more detail. So I'm going to ask this question, what is ground truth? If we ask Wikipedia for a definition, you get ground truth as information that's known to be real or true, direct observation and measurement, empirical evidence, as opposed to information provided by inference. I want to focus on that idea of empirical evidence rather than something that we kind of provide by inference. So where do we actually get ground truth? Well, it depends on the application, the context. In remote sensing applications, a lot of times it's what actually exists in the world behind the pixel that pixel represents. Okay, so that brings up another question. What exactly is a pixel? There's a famous paper by Albie Ray Smith that says it's not a little square. Okay, it's much more than that. And so if you imagine a typical scene where we have an image and we're constructing it as an array of points here, really that image is a bunch of sampled points on a grid. And so each one of those points is going to be a discrete sampling of the environment, capturing all the light that reaches that sensor. And all of this gets aggregated into a single value that we call a pixel, right? Okay, and so we can represent lots of things like color and other features with multiple images like this. So a lot of this is just, kind of preaching to the choir, I think, but it brings up another question. If we have an image that's supposed to represent ground truth, how do we actually define that? So imagine this scene here. That tree's kind of like not in the image. Oh, well, but imagine that tree is on the image. And each pixel is only able to get one ground truth value. So we might have a class label and a depth value that we want to assign for each pixel in this image. But sometimes it's not quite clear what to assign. So imagine a pixel here. This is in the sky. We're pretty clear that there's no uncertainty there. It's going to be really far away, effectively infinite. It's going to be sky class. A pixel down here is on a rock. It's also pretty clearly a rock. We might have a pretty good measurement of understanding how far away that is, 50. And now imagine that tree is kind of in the image there. I'm not sure why that got offset, but it wouldn't be quite clear what to assign if that tree branch was obscuring some of that rock. Is it part of the tree branch? Is it part of the rock? Is it, the close distance, the far distance? You can increase the resolution of that image to, give a bit more definition, but it doesn't really answer that underlying question. How would we define the ground truth for that region of space, that square that pixel is representing? Okay, so let's look back at where we actually get ground truth from. So a lot of times it comes from hand-labeled data, but how accurate is it? We often use simulation to say we get pixel level accuracy, we get pixel perfect ground truth, and we can sometimes use coarse labels. We get things like the COCO data set or YOLO data set uses bounding boxes. We don't necessarily need pixel perfect ground truth to be really effective at doing machine learning and AI tasks. But when we start to get into some of these other data sets, we get point clouds where we get nice segmentation. We start to assume that some of these ground truth images are more and more of truth than perhaps we should assign that type of credit to. So another way we can use or get ground truth is through simulation. So we can create synthetic data to provide ground truth. And we often think that this is going to be really good. So we can get object detections, for instance, with bounding boxes. We can get semantic labels through point cloud interactions. And the thing that we're actually going to focus on here for our application is the idea of getting depth from a simulated image. And as we're going to show, even that simulated ground truth isn't always perfect. So that's something that I want to dig into a little bit to understand in more detail. So we set up a couple of experiments here to really try and dig down into the fundamentals of what's going on when we try and predict depth from a single image. So this was a topic that comes up when you're doing those 3D point projections, if you're trying to estimate 3D space. But we wanted to focus on a really simple, basic example to understand these concepts. So we came up with this. We have a bunch of cubes that are in the foreground of an environment, and we have a background plane that's at a fixed distance. And we color the cubes red, we color the background blue and green. So in theory, you could train the network to learn, hey, red represents foreground, blue-green represents background. These cubes are going to rotate in space. We're going to shift the patterns just a little bit, just enough texture that we can identify some sense of scale, but nothing fancy here. And the idea is to try and get as simple a problem as we can just to study these questions of what happens when we define the ground truth, in this case, the depth, in a couple different ways. So let's look at a couple ways we can capture that image. We can look at an aliased version where every pixel is just a single crisp value. So every ray that casts out of the camera focal point hits an object, and we say it's either that color, it's that depth. And when we look at the 3D point cloud projection, it's pretty nice and clear. Another way that we could capture that data, if we're not careful, is we create an anti-aliased version of the image. That smooths out some of the sharp edges. But if we do that with the depth image, for instance, we're going to end up with issues like these trails in between the cubes and the background. Obviously, that's not quite right, but it does raise the question, in this image, that cube is just a crisp, flat line. So in truth, how would you define the depth for a pixel on that edge? So one of the things we thought about was, what if we just kind of create a bundle of all the possible depth values that edge pixel in particular could represent? So the way we accomplished this was we upscaled this synthetic image 10 times. So now every pixel in the original image actually has 100 values that we've sampled. And we're going to just lay those out in a big array. And so we get a histogram. I don't know if that's coming across clearly, but there is a histogram now of all the depths for every pixel. And so we get a bundle of all of the possible depths that a particular pixel could represent. So for our experiment, we're actually using ResNet depth network from the MonoDepth 2 implementation. The idea here is that we're going to generate a bunch of images at different depth backgrounds and train a network to learn that concept as well as possible. So it's almost a resubstitution type experiment. Not quite. We're doing an interleaved train test sets, but the idea is that we're going to try and learn as accurate a model as we can with this data set to learn this color image maps to this depth. Okay. So let's look at the first experiment that we tried. This is one where we use anti-aliased color and anti-aliased depth, and we know that this is not great. Our depth now is going to be right in the middle of the true foreground or background. But if we look at that prediction image, the input color and the ground truth depth, if we just use that grayscale mapping that we often see in depth prediction images, and we looked at the predicted output, we might say, hey, that looks pretty good. And it's not until we actually project those points out and dig into the details that we say, well, actually on the edges there, we're getting a lot of noise and artifacts that we don't like to see. So, if we dig into this a little more, here's an example of what happens when we look at just the background depth images that were at 60 meters away. So you can see we split the data into the set of pixels that were on the cubes exactly, on the background exactly, and all of the ones in between. And we get this distribution now where it's pretty good at predicting things on the cubes, pretty good at the background, but the edges are just this big, long distribution. We get those spikes there because of the resolution that we were sampling the depth at in the simulator, but you can see it's kind of spread over that whole space. So the next experiment we wanted to try was, well, okay, what if we tried that aliased version? So we now have an aliased color, an aliased depth. Each pixel now only has one single ground truth that's either the foreground or the background if it's on one of those edge pixels. We see a lot less points in the middle, and if we look at the distribution here, we get a bimodal distribution of those edge pixels. So what it seems to be learning is that the machine is picking one or the other values to assign depth for. So when it has an edge feature that it needs to assign a depth to, it's picking either the foreground or the background and less in the middle. Okay, so what about if we try this bundle approach? So now what we want to try is, okay, let's give the network all of that information, and our loss function now is going to try to minimize the distance to the minimum value in that bundle. So when we do this, we will when we do this, we see that the points that are being projected are still not perfect, but actually when we look at the plots here, we see, that's interesting. It looks like it's just kind of smoothed out that whole range there. And so what we think is actually happening is, even though we've provided all of that data, that ground truth information for the network to learn from, the machine has trouble actually picking what value to decide. So this was kind of a bit of a surprise to us, but perhaps can be explained if you think about it. The machine has so much choices to pick from. We haven't given it any guidance as to how to resolve that ambiguity when it has multiple values to pick from. So one last thing that we wanted to try, which actually turned out to be an error in the development process. We tried a different loss function that wound up doing the square operation outside of the min instead of inside the min. That was a mistake, but it turned out to actually introduce some bias into our experiment in a way that it was now preferring to predict close points. And so points that are closer to the camera, ones that are not as far away, are now preferred within that bundle. And so we've actually introduced some bias, even though we've provided all of that context for ground truth. We've now told the network how to prefer points that are closer. And so when we look at the distributions that we see here, the distributions for the edges in particular here are shifted now much closer to the foreground objects. And so what this is showing is that if we are able to introduce some kind of bias or some kind of guidance into our loss function to help the network understand, how should it resolve this ambiguity, we can see those appear in our results. Cool. So yeah, this brings us basically to our conclusions here. So yeah. Basically, simulation is great. It can help us with a lot of tasks with AI. We can think of using simulation to create ground truth, but a lot of times it might be better just to think of it as a gold standard and not the ground truth, because we don't always know what is really the truth. Anti-alias depth images definitely is something to avoid. If you're ever using depth images, make sure you're aware of how that's being generated in your simulation. Aliasing might be the solution, but it's also got its own issues, because we can't just assume that it's going to predict a near or far point, because that feature to the AI algorithm that you feed that image to may look at a feature and have no idea if what you meant was the foreground or the background in this case. So one way to approach this might be to use something like this bundled depth approach, where we actually provide more context to the network, where we actually understand there's multiple truths to one pixel. If you introduce some bias into that loss function, you can kind of guide it or help it to learn what you think is true, but this is something that we might be able to optimize in future work as well. So that's it. Thanks. I can take any questions.